In this lecture, we will be looking at examples of sequences and their convergence properties. Let's remind ourselves of some of the basics. First, the definition of an infinite sequence of real numbers is an ordered list, a1, a2, a3, a4. We call a sub n the nth term. In a previous lecture, we went over our definition of sequence convergence, and remember the idea is that the sequence an converges to the limit L, written this way, provided that we can get an as close as we want to the value L just by choosing n sufficiently large, by going far enough down the list. We also noted a theorem for the convergence of sequences and functions, and we saw that if your sequence is tethered to a function, and so we depict it this way, where the function has a limit as x goes to infinity of L. So this function has this L as the line y equals L as a horizontal asymptote. And the function defines the sequence by evaluating the function at the integers, or at least at the index values. So our sequence is here on the function itself. And the result of this is that the sequence has to converge as x goes to infinity to the same limit as the function. And you can think of this as the function is a road, and that road is converging to L as x goes to infinity, and these sequence terms are on the road. By taking the limit as n goes to infinity, you're just following these footsteps along the road, but they have to lead to the same place. What makes this such an important result is that it allows us to use everything we learned for the limits of functions when we studied that in single variable calculus as tools. So for example, if we want to look at the limit of the sequence 1 over 2 to the n, recall what that is. If we start at n equals 0, you would have 1 over 2 to the 0, or 1. 1 over 2 to the first. 1 over 2 squared. 1 over 2 cubed. 1 over 2 to the fourth. And looking at this, we intuitively can tell that this is converging to 0. And the way we would do this would be application of our limit laws. This would be the limit as n goes to infinity of 1 over the limit as n goes to infinity of 2 to the n, which we would call quotient law when we learned this in single variable calculus. And the top is approaching 1, and the bottom is approaching infinity, which means this entire limit is 0. So again, we're using the limit laws that we learned when we first studied limits in calculus. Another example, we also learned in calculus that because f of x is the square root of x is continuous for x greater than 0, we have a theorem that tells us that we can take this limit and bring it inside of that continuous function. So this limit becomes the square root of the limit as n goes to infinity of 2n minus 1 over 3n plus 2. And if you recall from your study of limits previous to this course, we kind of feel out what's going on here by saying the dominant term in the numerator is 2n. The dominant term in the denominator is 3n. For large n, those determine what's happening in numerator and denominator, and the larger n gets, the more insignificant the minus 1 and the 2 become, and the result is we should get 2/3. So we have a feel for what the answer is, but we use the approach of determining the leading term in the denominator and divide every term in the denominator and every term in the numerator by that leading term. And we identify the leading term in the denominator as 3n. So this becomes, inside the root sign and the limit, we have 2n over 3n minus 1 over 3n over 3n over 3n plus 2 over 3n. And application of our limit laws tell us that we have in the top limit as n goes to infinity, 2n over 3n simplifies to 2/3, minus the limit as n goes to infinity of 1 over 3n, over limit as n goes to infinity, 3n over 3n is 1, plus limit as n goes to infinity of 2 over 3n. And so we're applying both the quotient law and the sum law for our limits as we learned prior to this course. And we can then evaluate each limit, and we get the square root of this first term will be 2/3. The limit of a constant is just the constant. For 1 over 3n, as n is getting larger, we have a giant denominator with a fixed numerator, so that term is going to 0. For the first term in the denominator, the limit as n goes to infinity of 1 is, of course, just 1. And similar argument to the numerator term on the right, 2 over 3n, as n is getting huge, the denominator is getting huge with a fixed numerator, so that term goes to 0, and we get the square root of 2/3. And it's important to recognize that with this question, this is the question that you could have done with everything that you already knew from your limit studies and your previous calculus experience, because you could have just rewritten n to be x. Because again, this is a function, this is tethered to the function per our previous theorem. F of x is root 2x minus 1 over 3x plus 2. So whether you're looking at the sequence when you plug in n equals 1, 2, 3, 4, 5, although we'd have to start actually, yes, starting at n equals 1, that sequence will have the same limit as this function. Because again, think of the function as the road and the sequence as footsteps on it. They both go to the same place. So the techniques we used here are the same as what we already knew. This next example will demonstrate that further. So the limit as n goes to infinity of n e to the minus n as a sequence. So again, to remind ourselves that these are in fact sequences, if you start plugging in values, if we have n equals 1, you have 1e to the minus 1. If n is 2, 2e to the minus 2, 3e to the minus 3, 4e to the minus 4, so on and so forth. That's what this sequence actually looks like. And one thing we should notice here is that if we rewrite this as the limit as n goes to infinity of n over e to the n, we have a classic race situation. We have the limit as n goes to infinity of a polynomial versus an exponential. And from our studies of L'Hopital's rule, we know the exponential destroys the polynomial in terms of going to infinity faster. So we should expect this limit to be 0. But if we think of, how do we show that? If we think of So thinking of n as a continuous variable. And so by that I mean, instead of writing that this coincides with the function f of x is xe to the minus x, we don't necessarily have to write x. We can say, think of the n as playing the role of x. Then this function qualifies for use of L'Hopital's rule. So we see the numerator is approaching infinity, as is the denominator. So this gives the infinity over infinity indeterminate form. And thus, we can use L'Hopital's rule to say the limit of the quotient is the limit of the quotient of the derivatives of top and bottom. And again, we're thinking of this as now thinking of n as playing the role of x. The derivative of n with respect to n is 1, and the derivative of e to the n with respect to n is e to the n. And we now see the top is going to 1 and the bottom is going to infinity, and so we get an answer of 0. So you can see you can use all of these different techniques that you already know for limit computations, including L'Hopital's rule. And this comes in very handy for these types of sequence limit problems. And remember, anytime you do a limit of a sequence, really what you're answering is, as you go down this list, what are you actually approaching? If there is a limit, that's the number that you are getting arbitrarily close to by just going as far as you want down this list.